please welcome Pekka Janhunen, so researcher from...
Okay, thank you very much for this introduction, Andris. So let's go to the presentation mode now. So the topic of the lecture is, broadly speaking, how to inhabit the solar system. So, but before going to this subject matter, let's briefly discuss about Hannes Alfvén's legacy in this particular context. Of course, Alfvén did many things, and this is not the not the main thing that he did. But anyway, he also studied acceleration of charged particles in the cosmos, in the universe. I mean, how cosmic rays are produced, basically. That was kind of the research question at that time. And acceleration of charged particles is nowadays, it's applied. First of all, it's applied technically in electric rockets. So it means that we have some kind of basically particle accelerator which produces a particle beam which produces propulsion for the spacecraft. Then there is this electric solar wind sail, which is my invention, which Andris also mentioned. It's more efficient because it doesn't have to carry propellant. But in this context, what I'm talking about today, it does have the drawback that it doesn't scale to very large systems, so it doesn't scale to crude human missions. But it's very good for scientific missions. And then galactic cosmic radiation. So galactic cosmic radiation means very high energy particles, more than 1 gigaelectron volt particles typically, and one really needs several meters of wall thickness in order to shield against these particles. And the flux of these particles is rather low, so you can go to space and survive in this flux for half a year or perhaps a year, but not for a lifetime. So if you want to live in the space for a longer time, even your whole life, you must consider this shielding. Or at least this is the current kind of medical understanding what we have. So this galactic cosmic radiation is has a major effect on human space travel and space habitats. It's a kind of the hard boundary condition that we always have to think about when planning any kind of expansion out from the Earth. And this is exactly how the electromagnetic universe, what was kind of Alfvén's topic, how it affects us in very concrete terms. So not only the gravitational universe limits space activities, but also the electromagnetic universe limits it in this way. So then why consider moving out from Earth? So life, it's a basic property of life that life spreads. So every place is already, every ecosystem, every ecological niche is already taken because some individuals settle unusual environments, like this eagle owl is now inhabiting a very urban environment in the center of Helsinki. And life would certainly spread also outside of Earth if it just could. And other species cannot do it, but we just might be able to do it. So that's why it's kind of worth asking ourselves the question that, is it possible, is it feasible, is it worth doing? So often one speaks about Mars in this context. So, but my argument is that if you have, the problem with Mars is that the gravity of Mars is low. It's 38% of Earth's gravity. So if you have a settlement on Mars, then you have children on Mars growing their entire life on Mars. And then there is a great risk, I think, that the muscles and bones of the child would not become kind of normal in the development of the child, and then it might limit their ability to choose their living location as adults. So they might effectively become prisoners of Mars in that sense, they and their offspring. And this is a rather major, to me this is an ethical question, and when I see this kind of ethical question, I want to kind of understand if there are other ways of doing it. Is Mars the only possibility, and so on. So then we already know that in Princeton University, Gerald O'Neill in 1974 considered or he studied rotating cylindrical habitats using artificial gravity. It means that you have a rotating cylinder and people live on the on the perimeter of the cylinder, and they experience the centrifugal force, and it looks to them like artificial gravity. If the rotation radius of the cylinder is sufficiently large, then the centrifugal force is a good approximation for gravity. And then if we do such a thing, then we can select the gravity to be 1g, to be the same as on Earth. But this kind of cylinder, it has a maximum radius which comes from material strength restrictions. So maximum radius of, let's say, 5 kilometers or so. So it means that sooner or later we need more than one cylinder because we want to scale things up. And then we get into the problem of how to travel between the cylinders. And then, of course, the obvious answer is to use rockets. But then rocket propellant is a non-renewable resource in this solar system. So all the propellant atoms that you exhaust, they are permanently lost from the solar system because the solar wind actually, they get ionized by the solar UV radiation, and then the solar wind sweeps them out of the solar system permanently. So, and also we know the orbital dynamics is such that if you have a cluster or fleet of such satellites or objects in space, this fleet tends to spread along the orbit. So they go further and further from each other, making this travel between them more and more difficult. So to understand these problems, let's kind of list the requirements. What are the good requirements? I don't go through all of these, but just as an example. So we need cosmic radiation shielding. We need normal nitrogen, oxygen atmosphere. We need normal gravity. We need normal day length. We need agriculture. We need at least some local nature. We need some population density which is not too high. We need a large enough population in order to be socially stimulating. And then the system must be safe. First, safe, which means redundant, modular, and fixable, and preferably low-tech as much as possible. And then it's also possible that these kind of off-world systems could be better than Earth because they have no natural catastrophes. So they don't have hurricanes, they don't have wildfires, they don't have volcanic eruptions, they don't have earthquakes. And then the other thing is kind of the economical one, that potentially they might eventually provide even larger total living area than Earth itself. It might be hard to to imagine how it would be possible, but I will come to this point later on. And then, of course, one requirement is long-term sustainability. So all elements must circulate, which means, among other things, that we shouldn't rely on daily use of rocket propulsion. So let us consider this kind of geometry of a settlement. So we attach several of those O'Neill rotating cylinders to a rigid frame, and then we use bearings of some kind. The bearing at first sight, it sounds like a problem because it's a mechanical part, and then we are thinking about the wearing of the mechanical part. But this bearing can be done using magnetic bearings, so there doesn't have to be physical touch between the objects. So we can use magnetic bearings, rotating cylinders attached to this kind of very large frame. And then this thing is basically a disk which can grow. We can build around it all the time, so we can grow the disk in such a way. And these two clamshell type of things, they are mirrors. They are mirrors for reflecting sunlight into this disk. because eventually we want to use natural sunlight in order to grow our plants and agriculture in natural sunlight. And then one point is that Ceres, among all objects in the solar system, has certain important benefits for this kind of thing as a material source. So Ceres is a large object, about 1,000 kilometer diameter. It's the largest object in the asteroid main belt, and it has nitrogen. And nitrogen is a very critical element for any kind of space settlement, because air is mostly nitrogen, and we must need air to breathe on the space habitats. Of course, we don't consume the nitrogen, but we have to have it in the first place to establish the atmospheres. And although you might think that air is very thin, that it cannot weigh so much, but it actually does. So it is actually a critical resource, this nitrogen. And nitrogen is relatively rare in the solar system. Especially it's rare on asteroids, because it's a very volatile element, but Ceres has it. And then Ceres is a kind of large enough body. It has all very rich composition. All elements are there, not only nitrogen, but also carbon, iron, hydrogen, and so on. But it's not so large that lifting material from Ceres would be expensive. So Ceres gravity is 30 times less than for Earth. So it makes things like space elevators or slings feasible from Ceres. I mean, they are not feasible from Earth, but they are feasible from Ceres. So we would have this kind of disc-shaped what I call now from now on megasatellite, disc-shaped megasatellite in equatorial Ceres orbit, and then these mirrors, and then I mean, this is a bit technical detail, but you don't because you can make this mass distribution symmetric, you can eliminate tidal torques of Ceres, what would otherwise kind of exist in this system. And then I was talking about natural lighting. So here is a concept how you can basically by 4 reflections altogether, you can reflect sunlight in such a way that you can get natural looking sunlight. So you get the same intensity of sunlight as on Earth, and you get it into the habitat, and you get it in such a way that you don't get this galactic cosmic radiation in at the same time. So you focus the sunlight using a parabolic mirror, and then it goes through a narrow slit. It's not really narrow, but it's narrow compared to the size of this system. It goes through a slit, goes around the corner, and then reflects downward, and then makes yet another reflection, which finally produces the illumination on the agricultural and the natural fields that you have there. And this going around the corner is enough to ensure that you don't get space radiation, this galactic cosmic radiation in, because that radiation doesn't reflect from mirrors, it propagates straight, so it doesn't go around corners. And the outer shell of this cylinder here must be several meters thick in order to shield this from the galactic cosmic radiation. But this material we get from Ceres, and it doesn't cost so much. Here is a picture of that megasatellite. Here is a more closer picture of that megasatellite. So the cylinders are here, the narrow slit is here, it's just a small, not very well visible. And then these black things down here are the parabolic mirrors. I will show later an animation, an interactive animation of this thing, so then we will return to this a little bit more carefully. So then we can have diurnal cycle, which means that we have a similar sunlight pattern as we have on Earth. We can do that with 3 time zones, which have plus minus 8 hour time differences between them. And this is kind of the explanation how it will be done it requires that you have kind of movable ceiling on each of these 3 zones, and then you can simulate nighttime and dusk and dawn and daytime. And you also need blinders here in order to block sunlight during the night. And the point here is that this sum of light across this time zone is constant, so it means that all the sunlight is utilized, so there is nothing wasted. Yes. And then thermal design, I don't go into details here, but you need, like usually in space systems, you need, even on ISS, you need liquid transfer of heat. And also here you need some kind of fluid transfer of heat across this artificial soil and this artificial radiation shield. And then it's kind of interesting that even at Ceres distance from the sun, which is 2.8 astronomical units from the sun, one would think that it's very cold up right there, and the sun is almost 10 times dimmer than it is here on Earth, but still cooling is a bigger issue than heating, even on Ceres. And the dimness of sun is not a problem, because we can always compensate that with these parabolic mirrors. So even if this would be much farther away in the solar system, we could still apply the same engineering. We would just have to scale those parabolic mirrors in a different way, so that these cylinders would sit somewhat further apart from each other. And notice that these mirrors and parabolic mirrors, they are very lightweight, because they all sit in microgravity. They are not under the centrifugal force. They are not under centrifugal force. So almost all the mass in this system is in the radiation shields and in this artificial soil here. Then travel inside this megasatellite, it must be easy. So again, I don't go into details here, but I just mention that we can travel inside the megasatellite, especially using some kind of trains or buses, whatever you want to call them, which move in tunnels in microgravity. And things are straightforward, especially if one is happy with the passengers experiencing microgravity during the trip. But if you want to avoid that, then it might be possible, but it becomes more complicated. And this is a question that how well people adapt to this microgravity, and this is something which we don't really know very well yet, because we don't yet have this general space tourism so much that we would have experience of how completely ordinary people adapt to microgravity. And then, yes, each of these cylinders is a closed ecosystem, or it might be actually sectioned into several ecosystems. And then, of course, this is naturally flexible and compartmentalized, so that if there is some problem in one cylinder, for example, if there is some disease or some illness, some microbes spread in some one cylinder, then one can block this cylinder out of this community, and so on. And then if something goes very badly wrong in one cylinder, then you can take people out, and then you can stop the rotation, and then you can do anything you want with the cylinder. You can rebuild it, you can recycle the materials, whatever you want to do. And then the mass budget of this megasatellite. So here we have an assumption that we have 2,000 square meters per person, which is kind of distributed about 50-50 to sunlit, what I call rural landscape, and then urban space, which is artificially illuminated. So most of the mass, 69%, goes into radiation shielding. Then soil and biosphere take about 25%. Tensile structures, which is the non-trivial thing here, is only 5%. then air is 1%. So, and most of this air is nitrogen. So nitrogen is about a bit less than 1% of the total mass, but it's a very critical ingredient, because without it we cannot really survive. You might ask a question that couldn't one use purely oxygenic air with reduced pressure, because such a thing has been tried at some point on space stations. But the answer is that for long term, at least my opinion about it is that for long term living it's not a feasible approach, because it would increase the fire hazard too much. So that's one thing. And it might also too much increase like oxygenic stress to the lungs of the human lungs, and it would also make it very difficult or maybe even impossible for insects and birds to fly, because the air is too thin for them to stay aloft. So these kind of things, and I think we need insects for pollination of plants. We need birds, because we humans like birds. We need them for that reason, at least. So and then the production energy, most of the energy budget of making this kind of structure goes into making the tensile structures. And then one important point here is that nothing needs to be abandoned on Ceres. So you can mine material in sequence from Ceres. You don't have to select anything. You just mine material, lift it up, and then analyze the content once lifted, and then depending on the content you use it either as structural material or biospheric raw material or everything else you put in the radiation shield, because radiation shield doesn't care very much about the elemental composition. There is some dependence of the so light elements are better at radiation shielding than heavy elements on average, but the differences are not large, and if you can always compensate it with a little bit thicker material. So in this sense, this radiation shield can be your waste basket, and this is kind of important because it enables you to consume everything from Ceres in order. You don't leave any waste piles on the surface of Ceres, which would be nasty because they would interfere with future generations, increasing this construction. Okay, then like calculation that what are the limits of this approach? So Ceres is very large, nearly 1,000 kilometers across. So there is a lot of almost infinite amount of material in Ceres. So we need about 10 to 7 kilograms per person of material. That means 10,000 tons per person of material. And the production energy per living area is this, and then 10 to 13 joules per person of this, making this structural material. It's a large amount of energy, but you need it only once in order to create the living space for this one human being. So, for example, if you build a satellite for 10 to 11 people, that means more than 10 times the world's current population, 100 billion people. You need only 1,000th of mass of Ceres. And then the growth rate here, I don't go into details, but I just made a calculation exercise that if you cover like a significant fraction of Ceres by solar panels, then how much power you get, how much material per year you can lift with that amount of energy. And this boils down to 300 million new immigrants per year. So the availability of sunlight and solar power at Ceres is not really a limitation. It can support very high growth rate also of this kind of settlement. But then travel to Ceres is a challenge, as you might guess. Ceres is 2.8 astronomical units from the Sun, so travel to Ceres takes longer and requires more delta V than travel to Mars. And it seems to me that one almost necessarily needs some kind of electric propulsion, so that chemical propulsion is not really good enough for going to Ceres. You can go to Ceres with chemical propulsion, but not very well. So if you want to have short enough travel time, then you almost certainly need electric propulsion. And that means that you need some electric propulsion engines which use cheap propellant like water or oxygen, because the current ion engines use noble gases like krypton and xenon, but these are too expensive and too rare even on Earth, and they are completely absent in asteroids and in Ceres, because noble gases, because they don't form any compounds, they have disappeared, they have evaporated a long time ago from any small bodies of the solar system. And then if one considers that if Ceres is too far for present technology for kind of human migration, then one could practice this in a little bit smaller but still large scale using the orbit of Mars. So build this kind of megasatellite in orbit of Mars using Deimos. That's one of the moons of Mars, using Deimos as a source body. Or you can also use Phobos, which is another moon, but Deimos is kind of better in this case because it's not too close to Mars. And in this way you can kind of support like a few tens of millions of people at most. So this is the scaling limit for Deimos. With Deimos we don't have the scaling argument that we could inhabit 100 billions or hundreds of billions of people, but with Deimos we could inhabit a few tens of millions of people at most. So these are the kind of the boundary conditions. So then after discussing this, let's turn the question around, what's wrong with the Earth, or is there anything, is there something wrong with the Earth? Why ever to consider this kind of off-world, off-Earth living? So one point of view is this, that living on Earth means in some sense fighting against the seasons. So you have to store food and energy for the winter, you have to transport goods and food from far by ships in many cases. You suffer from bad weather occasionally, you have a dry season or you have flood and so on. And at the very top level, life, including humans, any kind of life needs three things. It needs energy, water and nutrients. But Earth, it has all three of these, but in combinations which are such that there are not so many places on Earth where all three of these ingredients are overlapping. So for example, continents have nutrients and light, but then water is a bottleneck in many cases, or at least it's irregular. And then sea surface has water and light, but it lacks nutrients because of the thermal stratifications of the oceans. And the sea floor has nutrients and water, but no sunlight. So, and we are on Earth we are used to living with these challenges, but if we go to this kind of megasatellite, which is a technical system, completely engineered system, then we can optimize these three ingredients so that we would always overlap these three ingredients of life. So on a megasatellite there is no energy problem because the sun shines all the time. And as I mentioned earlier, the fact that the sun is far away, 2.8 AU, is not a problem because in microgravity, in weightlessness, parabolic mirrors are lightweight. You can make them lightweight as soon as you have a capability to manufacture and assemble things in orbit, which of course we currently don't really have. But if we consider any of these kind of systems, we are all the time making the basic assumption, of course, that we can assemble things in orbit. And then there is no need to store food because you get food all the time. The plants themselves keep the air clean, so they circulate the gases that and waste what we produce, what humans and animals produce. And then, as I mentioned earlier, no volcanoes, no earthquakes, no hurricanes, no tsunamis. Perhaps no resource competition, unless some human beings kind of artificially create such scarcity. But in principle, because I mean the resources are on Ceres and they are almost unlimited. You just have to lift them up, and then the other resource is sunlight, which is everywhere, which is not a limitation. Then you can always enlarge the megasatellite. You don't have to compete for someone else's living space. And then one kind of interesting thing from the universal point of view is that this kind of megasatellite is about 1 million times more mass efficient way to produce living space than a natural planet, because on a megasatellite we have about a few meters or 10-meter thick wall between us and the vacuum of space, and that's for maintaining the centrifugal force, maintaining the artificial gravity, and enclosing the pressure, and then blocking the galactic cosmic radiation. Whereas on Earth we have 6,000 kilometers of molten rock below our feet. And this rock is doing nothing except it just maintains a gravity field which prevents the air from escaping and produces the gravity field what we need for living. And but we can do this both by engineering in this kind of habitat. So we enclose. We don't need gravity to keep our atmosphere because we just have solid walls which keeps them, and then we don't need mass to produce gravity because we can use the centrifugal force to produce gravity. And both these arguments kind of bring the result that it's really a factor of millions. So this is also kind of interesting from the point of view of life in the universe. So if there are technological species in the universe, then perhaps they live in such systems mainly, not on planets, but because it's more efficient. Okay, so then I also, in my abstract, I promised to discuss a little bit about lunar resources, which it's a little bit sidestepping here, but so for any large-scale space project like this, one needs orbital construction, and then the moon is a nearby source of material which has much lower gravity than Earth, so it's easier and cheaper to lift material from the moon than from the Earth. And it's even better if you can lift material from the moon without rocketry, without using rocket propulsion. And you can use a thing like a sling or an electromagnetic gun, but let's say sling, you can sling a projectile from the moon, but the only problem is that if you sling a projectile, then it falls back on the moon at the same point where you sling it from. And this is something that already Newton realized, or at least it's attributed to his name. But however, the moon has something called gravity anomalies, so its gravity field is irregular, and we found recently that by using just selecting the launch location in a suitable way, we can make the gravity anomalies of the moon to conspire for us in such a way that this projectile stays in lunar orbit for up to 1 week. And this 1 week is sufficient time for an electric propulsion satellite to rendezvous with it and grab it, and then carry it using efficient electric propulsion to some other orbit. And in this way, our old moon could be turned into a material source which is technically almost as simple to use as asteroids, but it's much closer, and it's almost unlimited. So this could be like a way that might help bootstrapping this kind of large space project, not only the Ceres or Deimos, but anything. Here is the map of the gravity field of the moon, so it's really irregular, as you can see. The irregularity, the physical reason for that is that these lots of craters that exist on the moon, they are kind of the reason why its gravity field is so irregular. Okay, so here are my conclusions, but before quitting, I think I have still some time to show you this animation. So this is like a JavaScript visualization, interactive visualization, which runs on the web. So you can play around with it with any browser that you have. This should work. So there are two mirrors here, which are reflecting everything that is visible in the universe, but including the sunlight. And then we have this megasatellite here. We can switch the. I mean, the illumination level here was selected for visualization. So actually, it looks like this. I mean, the sun shines exactly in the plane of the megasatellite, so it actually illuminates only these some of these cylinders. So this is how it would look actually, and then we can zoom in a little bit, and then we can make it a bit larger, so it grows in this way. We can add also smaller cylinders, so all these cylinders don't have to be the same size. I have just drawn them the same size for simplicity. And then we can also add this kind of other facilities, factories there. I mean, microgravity factories there. Not everything must be in these living cylinders and so on. So you can kind of see how this system would look like in this setup. And you can zoom and so on. Yes, okay, so that's that. And then let's go back to the presentation. So conclusions are here. Earth is the only planet, probably Earth, I would say probably Earth is the only planet where we can meaningfully live. But that doesn't mean that, I mean, we can still consider unplanetary living, such as in this Ceres megasatellite, which has a permanent benefit of no natural disasters. And the other benefit is the scalability. So there is this factor of million mass efficiency compared to planet. So that's why it's potentially scalable to much larger living areas than Earth provides. And long-term sustainable, all atoms circulate, and this moon bootstrapping might be possible. Here are references and acknowledgements. So I think I end here, and I'm happy to answer your questions after this. Okay, thank you.